Welcome back, everyone. We are still working through, what is this, unit? We in unit 12? 12? 13? 12? Unit 12 it is. All right, sounds good to me. Yeah. The last thing that we learned yesterday was how to work with the sum and difference identities for sine and cosine. And I think it might be beneficial for you to see these identities written as a single statement and see the symbols that mathematicians use. So here we have the sine ones, and notice that the only difference is the symbol in the middle changes, right? And whatever symbols between the two angles matches here and here. That is going to give me the ability to write this as a single statement that looks like this. And you might be saying to yourself, but how is that beneficial because cosine is going to do the exact same thing? I go, well, it doesn't. Because here, cosine is going to have the opposite symbol between your trigs. So that formula will be slightly different symbol-wise. The way that mathematicians say use the opposite symbol when you have two like that is they flip it upside down. So if you see your plus minus symbol upside down, that means, oh, use the opposite of what you had in here. If you see it right side up twice, that means use the same symbol. But why even bother? Because I told you yesterday that whenever you're going to use one of these identities, you should probably write the identity down. And so instead of knowing it as two different identities, you can know it as one. Same symbol. So when I get to an example like number 11, is it number 11 I was thinking of? Oh no, I'm thinking number 13. Well, whatever. We'll hold on to that until we get to number 13. Here we're saying sine of the sum of two inverse trigs. And this makes sense because the result of all inverse trig is an angle, right? Tangent inverse of 1 says there is a triangle, there is an angle, either in quadrant 1 or quadrant -1, where the y over x equals 1. Well, the only way that they're both going to be, the only way it's going to be positive is if they were both positive in quadrant 1. There it is. So there's my y, there's my x. So this triangle is created by tangent inverse of 1. It makes this triangle. This says there is an angle somewhere, that means there's a triangle somewhere, where the x over r just gives me back x. That's a positive x. Cosine inverse can only give me back things in quadrant 1 and 2. It's only positive in quadrant 1. So we draw a triangle, x here, 1 there. Okay. This triangle is created by cosine inverse of x. Good deal. Do you remember when we were writing equations for sine inverse, cosine inverse, tangent inverse with x's involved? Like if I said, hey, what is sine here? You would have to know this number, right? Let's go ahead and get this triangle fully filled out. I mean, this one has all three sides. Let's get all three sides on this one. How am I going to find this missing y value? Pythagorean theorem. X squared plus y squared equals r squared. but our r is 1, so 1 squared. Let's get y by itself. And because we know we're in quadrant 1, y must be positive. There it is. Cool. We are ready to use the sine sum identity. I'm going to write it down, and I'll just write the plus sign. No way around it. You are going to have to memorize this identity, or some of the identities, and leave yourself memory breadcrumbs to build the others. But this is the sum formula for sine. In this scenario, this is alpha. This is beta. See, alpha plus beta. So when we fill this thing out, we're going to get sine of alpha cosine of beta plus cosine of alpha sine of beta. And then we go to work. Alpha is this angle right here, created by tangent inverse. What is sine at that angle? It's 1 over root 2. This is quadrant 1. You know what cosine and cosine inverse do to each other in quadrant 1? They cancel each other out. All trig and its inverse cancel each other in quadrant 1. So it's just x, because cosine and cosine inverse cancel. If you weren't sure, you could say, what is cosine here? You go, oh, it's x over r. Oh, x over 1? X. Okay. Plus cosine at this angle. Oh, 1 over root 2 again. Sine at this angle. Y over r. Square root of 1 minus x squared. This is going to get me x over root 2 plus root 1 minus x squared over root 2. I could write that as one fraction, right? And to rationalize the denominator, what am I going to do? Yep. Multiply the top and bottom by root 2. Now, you might have noticed when checking the answer key for the homework, if you've been working ahead, that for the sum and difference identity style questions we had to evaluate, she had her answers factored. And here's why. When I multiply the top and bottom by root 2, I could say it's root 2x plus root 2 times root 1 minus x squared, which actually moves the 2 inside the radical, or I could just leave it like this. I think that's easier. In the homework answer key, you would have seen things that looked like this. Which is root 6 plus root 3. Or I think this was a 2. The point is, if you would like to leave it factored, you can. If you would like to distribute it, you can. For the numbers, I like to distribute, but for what are these things called? Expressions, I leave them factored. Because distributing that root 2 doesn't clean anything up. What do you think about all that? Can you do that? Use the identity and put it together with the skills that we did in the last unit? Awesome. We're going to find exact values for sine of 2 theta and cosine of 2 theta given only this information. We know that cosine of theta is going to give us 3 over 5, and we know we're in quadrant 4. Cosine is x over r. How would I find the missing side? Pythagorean theorem, but what is the missing side? It's almost 4. What is it? Negative 4. Because I am in quadrant 4, where y's are negative. This is the Pythagorean triple of 3, 4, 5, right triangle. Pythagorean triple. It means a right triangle where all 3 sides are whole numbers. Well, all 3 sides are integers. Cool? Okay. It's the most famous Pythagorean triple. It's not the only one. We need to find sine of 2 theta. The formula for that, which is in this packet, is 2 sine theta cosine theta. So, 2 sine at this theta, by the way, this is theta. Sine at this theta is y over r. And cosine of the theta was given to us. Two times 4 times 3 is 24. We're just filling in the identity. That's all we're doing. There are 3 different cosine double angle identities. When I don't have to pick a specific one, I always choose this one, because it'll always give me a common denominator. Whereas the other ones that say -1 or 1 minus, then I have to find a common denominator, and I don't want to do that. I'm being lazy. Cosine of theta is 3/5. It was given to us. And we just said sine of theta a moment ago was -4/5. And we're going to square it. So 9 over 25 minus 16 over 25 is -7 over 25. Wait a minute. Sine is y over r. And cosine is x over r. That means this x, this y, and this r, 7, 24, 25, is also a Pythagorean triple. How neat. 7, 24, 25. Guess what else? You don't know what theta equals, do you? But you do know that both sine and cosine of, I just realized there's no 2 here. You do see that doubling the angle for sine and cosine gives you a negative result, right? Where would both sine and cosine be negative? What's that? 3rd quadrant. So if you double this angle, you're over here somewhere. And it, since y is longer than x, it's like this. 7, 24, 25. It's less than, no, this angle's already in the 300s. So if you double it, you're in past the 600s. Yeah, so it's past 540. but less than 630? Yeah. Crap. I'm so bad at this. But anyway, there it is. What do you think? Know the identities? Pythagorean theorem. Fill out the identities. Not that bad, right? Not too scary hard. You do have to memorize a lot of stuff. Holy guacamole. A shifted sign function added to a different shifted sign function, and we're trying to figure out where it equals 1 by hand. Whatever shall we do? I'll tell you what we're going to do. We're going to use the sum identity here and the difference identity here. What just happened? Why did she make you get a phone charger for her?
Okay, because I was like, hey, do you have a phone charger? Because I didn't want to bother your lesson.
Oh.
And she's like, you can just go up there. I'm like, oh, no, I feel bad. Like, he's teaching me. She's like, no, it's fine. I'll do it for you.
What the heck? Oh my gosh. Like I wasn't going to ask? That was the weirdest exchange. Okay. Anywho, let's fill this thing out. We'll do the left one first. It's going to go sine x cosine pi over 3. Same symbol, plus cosine x sine pi over 3. So that's the first one. Now the second one is the difference identity. Sine x cosine pi over 3. Same symbol, minus cosine x sine of pi over 3. And this equation still set equal to 1. So this is not an identity that we're trying to verify. We're trying to solve for x. And look at this. Boop. These two guys right here cancel each other out. Bye-bye. Bye-bye. There it is. Much simpler question. Wouldn't it be great if we knew what cosine of pi over 3 was? No calculator. Pi over 3 is 60 degrees. Let's fill out this triangle. Cosine here is 1/2. Two times 1/2 is 1. So this question boils down to, when is sine of x equal to 1 on the first circle? Sine is y over r. So the only way we get a 1 is if y and r happen to be the same number. Pi over 2. Woo! There it is. Could we figure it out just by looking at it? How did you get pi over 2? When sine is 1 normally?
that the differences between them cancel out?
No, it's coincidental. Yeah, no, you can't do that. And the only reason why it actually worked is because this is a maximum. But if we had set it to equal to anything other than a maximum, it wouldn't have worked. Next, solve them for x. Check it out. A double angle. We have identities for sine of 2x, don't we? Just one of them. The double angle identity for sine is 2 sine theta cosine theta. That means we can replace sine of 2x with 2 sine x cosine x. So we just made a replacement. We substituted in for sine of 2x. And we're trying to solve this thing. It happens to be set equal to 0. One of my favorite F words. Factoring. Cosine of x is your GCF. So you can just set your parts equal to 0 now. We will figure out where cosine of x equals 0. And we'll figure out where sine of x equals negative 1/2. Cosine is side length x over side length r. The only way that fraction would have a value of 0 is if there was no x side length. In the first full circle, where is there no x side length? The y-axis, which would be pi over 2 and 3 pi over 2. We have no x's there. Well, no side length x. So those are our answers there. And in the first full circle, sine is negative in 2 quadrants, 3 and 4, because that's where your y values are negative. My voice is struggling. These are 30-degree angles because they're across from a 1 in a 30, 60, 90. But 30-degree angles are pi over 6s. So let's write out our answers in numeric order. The first one as we traverse our circle is this one, pi over 2. The next one is here at a pi over 6 after pi. Then here at 3 pi over 2. And lastly, a pi over 6 before 2 pi. 11 pi over 6. Alrighty. We good? Factoring. It's going to come up. Now this next one does not inherently look like any of your identities, but you could make it one. What would make this one of our identities? Yeah, if there was a 2 in front of that sine x cosine x. So I'm just going to multiply both sides of the equation by 2. Because this 2 sine x cosine x is the double angle identity for sine. So 2 sine x cosine x is equal to directly sine of 2x. Oh, and half of 2 is 1. This is now a question that we did last unit, where we have to make a substitution and stretch the domain. Yay! It didn't. This, remember the identity is, it didn't go away, it's part of the identity. These 3 things multiplied together equal that. I'm going to make a substitution. So that it says sine of theta is 1. But if I make a substitution in the function, I have to make a substitution in the domain. I have to stretch that domain out. So if I double, boop, 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 all 3 of those things, I can now make the substitution. So I'm trying to figure out where sine of theta would be equal to 1 in the first 2 circles. Well, we just said sine was 1 at pi over 2. That's in the first full circle. But we have to go around twice. So there are 2 answers for theta. The first 90 degrees is pi over 2. But if you add 2 pi to that, that's adding 4 pi over 2. You get those 2 answers. But we're trying to solve for x. And remember, theta was 2x. Multiply everything by 1/2, and what you'll get is x equals pi over 4 and 5 pi over 4. So sometimes you don't need a factor. Sometimes you just need to force an identity. Want to ask me any questions about that one? Okay. This is polynomial in nature. And hopefully you see that right there. And you have 3 options for this double angle identity. But no matter what, there's going to be a sine x here. That's the giveaway that you don't want 2 kinds of trig in the equation. If you can avoid 2 kinds of trig in the equation, that's what you do. You try to avoid 2 kinds. Which means I don't want to have cosine here. I can't do anything with that. But there's a substitution I can make for this that does not involve cosine. One minus 2 sine squared theta. You have a question? No, just stretching. You too? Just stretching. Okay. See, if I replace it with that, I only have 1 kind of trig, sine. And that makes life good. Let's make the substitution. Replacing cosine of 2x with this. Combine like terms, the 1 and the minus 2. And kind of bothers me when my polynomials have a leading coefficient that's negative. So if you just divide out a -1, or if you multiply everything by -1, you'll get this. And my favorite F word, this factors. This does factor. The two numbers that multiply to 2 and add to -3 are -2. Did I say that backwards? The two numbers that multiply to 2 and add to -3 are -2 and -1. So either know how to factor using Lizzie method or AC method or whatever method you want to use, but it factors like this. Factored. So you set the parts equal to 0. And you can solve for x. This one will happen when sine of x is equal to +1/2. And this one, when sine of x is equal to 1. Sine of x is positive in the first two quadrants because that's where y values are positive. So since they're across from 1s, those must be 30-degree angles. So pi over 6s. And we've seen this one a few times today. +1. So only pi over 2. So our three answers in numeric order are the first 30-degree angle, pi over 6, then pi over 2, and then 5 pi over 6, and there they are. Now, we only have 2 examples left. I can't get both of them done in the remaining 12 to 13 minutes. I could easily get one of them done. But that would mean that our lesson tomorrow is 1 question. This is where I stopped with period 2. So that's where I'm going to stop with you guys as well. Tomorrow, we will do those 2 examples, and you'll spend the rest of the class period working on your homework, getting help where you need it. And what will be awesome is if you got all the work done tomorrow in class, because you've already got most of it done, right? Right? Yeah. That way you have no homework tomorrow night. And then you could spend your time, playing Call of Duty or all that other stuff that you guys do. Thanks, nerds.